So today we're going to be talking about the Riemann zeta function. Now we're going a little off topic here, but let's just do it. So the zeta function is a function of a complex variable that analytically continues the sum of the infinite series, and it's convergent, which means we can get values, as we shall see later. So this is the general form, zeta of s as it's summed over 1 by n to the power s, and s here is a complex number as Riemann introduced, and the original Euler function, if we take s is 2, we can get this sum which equals pi squared over 6, which Euler showed beautifully. Now the function can also be represented as a product of primes, which is again really important. It shows that it encodes fundamental information about the primes. It's a product of primes in this notation, and as we've seen, this is only applicable when the value of s is greater than 1. So if we try, but the zeta function is a holomorphic function, which means we can analytically continue it, and this is the new form we get where it's greater than 0. Now this is an alternating function, and now let's see what happens if we try to take the value of s as negative. Now we get this fancy formula here, which is actually simple to understand, but basically what we see here is the mirror term, which means there's a symmetry line which lies in one half, but we'll come to that later. There's a symmetry line, so any positive value you get can always be reflected onto the other side to get the negative value. Now let's look at the famous problem of 1 plus 2 plus 3 plus 4. You may have heard of the controversial result that it is equal to minus 1/2. We can actually plug that into the zeta function and get the value. So take the zeta function where s equals minus 1, so 1 by n to the power minus s. So just take the reciprocals of all of them and you just get 1 plus 2 plus 3 plus 4 plus 5 plus 6 and so on. So by simplifying this term, we can get 1 minus 1 by 2 pi squared, and we've shown that this is nothing but 2, and zeta of 2 is nothing but pi squared over 6. Now the pi squares cancels out and we get nothing but minus 1 over 12. Now this seems very controversial, but it actually isn't, and we can come to that in a later video. Now, as you've seen, this part after 1 is this, every point on this is a complex plane. As you can see, the number line in the complex line. So every point here on the complex plane has a value, whether it's on the positive side or the negative side, but there exists this one band between 0 and 1 where the values are undefined. So there is something called, so let's look at the values for which the zeta function is 0. Turns out that every even negative number is a 0 of the zeta function, but these are all trivial zeros. What we're interested in are the non-trivial zeros. Turns out there are an infinite number of non-trivial zeros between this one band. Now the famous Riemann hypothesis is that all of the zeros lie on this line. So basically all the non-trivial zeros of the zeta function lie on half plus it or half plus I something, where half is the real part of the number. Now thanks for watching, hope you liked it, and stay tuned for more physics videos returning.